in listen-only mode.
So we have started, Mars.
Okay. Dear participants, good afternoon, good evening, and good morning. It's a great pleasure to welcome you today to our fourth webinar of 2015. Earlier, we hosted webinars on various topics. APQI, or the Asia Power Quality Initiative, is an independent, neutral platform that aims to build awareness and capacities on issues related to power quality in Asia region. This Pan-Asia platform, supported by national support network partners, continues to carry out activities towards capacity building and awareness creation amongst various stakeholders. We work further to facilitate regulatory and standards initiative in respective country. Our website apqi.org is supported by Leonardo Energy Europe and is the single largest resource for discussion papers, research and data on power quality in the countries we work. We work with a focus on shared learning, transparent exchange of information, and active engagement in this area. In increasingly digital world of today, the sensitivity of plants, process, and equipment demand for high power quality environment. And poor power quality can impact severely both in terms of economics as well as safety. Power quality in the low voltage and medium voltage network and end user premises, especially industries, is largely not measured, and unscientifically it is not well understood. In more than one sense, for many business or industrial users, the cost of poor power quality could be higher than their electricity bill. And the issues are still largely underestimated, mainly because the losses are often hidden or not known. With the growth in the use of our electronic equipment, it influences power quality further in two ways. Powered electronics, built-in computer supplies, energy-saving lamps, motor-driven systems with variable speed control are generating first harmonic disturbances. Due to the prevalence of these systems, nearly all electric grid nowadays suffer from harmonic currents. They result in additional heat losses and premature equipment failure. Second, the very loads that disturb the system are themselves increasingly sensitive to power quality disturbances. And when electronic equipment suffers from voltage dips, outages, it can result in lost production, damaged equipment, idle personnel, and lost data. Singly or combined, these effects can lead to postponed revenue and a negative impact on cash flow, loss of goodwill from customers, and even loss of market share. So very few industrial sites are trouble-free, and most suffer from several PQ issues at once. Keeping the above in mind, I welcome you all on behalf of APQI India to this webinar, How to Calculate Electric Losses Due to Poor Power Quality. Our distinguished industry and utility experts from IIT Delhi and Fluke will talk about various issues we face. We will learn what and how to arrive at losses due to poor power quality, facilitating better decision making, and our experts will share their thoughts on above issues. Our experts today, Dr. Bhim Singh is a doctorate from Indian Institute of Technology, Delhi. In 1983, he joined the Department of Electrical Engineering, University of Roorkee, and in December 90, he joined the Department of Electrical Engineering, IIT Delhi, India, as assistant professor. Since October 2012, he is the CAA Chair Professor and presently Head of the Department of Electrical Engineering at IIT Delhi. His fields of interest includes power electronics, electrical machines, electrical drives, power quality, solar photovoltaic, energy conservation systems, wind energy conversion systems, small hydro system, FACTS, and HVDC transmission systems. Our second expert, Mr. Frank Healy, Global Product Marketing Manager, Fluke Corporation, has been actively involved in power measurement and power quality for almost 30 years. He started in UK as a hospital engineer at a large metropolitan healthcare facility specializing in electrical and electronic systems. Later, he worked as an instrumentation application specialist for Siemens and has been involved in a variety of roles in supporting and consulting for electrical testing and power quality applications. He has written and presented a number of papers for national and international conferences in Europe on the subjects of power quality and electrical grounding. Since 2006, he is working as Global Product Marketing Manager for the Fluke Power Quality Business Unit based in Everett, Washington. Frank currently resides in UK. Before I go ahead, some housekeeping measures. All the attendees kindly keep your mobile in switch off and little bit away from the system on which you are attending the webinar. We'll have both the experts' presentations one after another, 30 minutes each. During that time, you all will be muted. If you have any questions or clarity you needed, kindly put it in the chat box. On your right hand side, you will see there is a chat box, and post it to us so that we will be able to take that up with the speakers, expert speakers. After the presentations are over, then we will have question and answer session over 15 minutes. We would request you to put your question and also mention to whom you are addressing that question. That will help us to redirect the question to the experts who will then respond, and at the time of question and answer session you will be unmuted so that you all can hear very clearly them. So with these housekeeping measures, I sincerely hope we will experience a good discussion in today's session, and looking forward to your active participation in future too. Please do participate in the survey after the webinar is over. Thank you. Now I hand over the floor to our first expert, Dr. Bhim Singh.
Well, good afternoon, good morning to all of you. I'm Bhim Singh. I'm going to talk about typically on the topic how to calculate electrical losses due to poor power quality. Well, to start with, as an introduction, due to power quality problems such as low power factor, unbalanced loads, neutral current, nonlinear loads in the distribution system, the losses are increased, thereby reducing the efficiency of the power system. The mitigation of these power quality problems results in reduction of losses in the distribution system. So the estimation of electrical losses in distribution system without and with compensator are analyzed using the different cases. Well, the present table shows the power quality problem causes and effects. There are a number of power quality problems like related to transient, which have a maybe nature of impulsive and oscillatory, and they cause the resonance in the power system as well as system resonance. Another kind of problem is short duration voltage variations such as sag, swell, interruption, and they cause the disturbance typically for protection malfunction, loss of protection, swell also in the same way, as well as interruption cause the loss of protection and wrong operations of fire alarm. Another power quality problems cause long duration voltage variation of the kind of sustained interruption, under voltage and over voltage, and they cause lot of loss of production, increased losses, heating, damage to house and household appliances. Of course, the region also mentioned here that what may cause the under voltage and over voltage also. If we go to the next slide, we have a waveform distortion, may have a DC offset, harmonics, interharmonics, notching, noise. And first one is of course in voltage imbalance. That causes the heating of the typically of AC motors like induction motors. Even like a 1% unbalance in the voltage normally cause 6 to 7% unbalance in the current because of the backward field impedance is quite low, which is 1/6 or 1/7 of forward impedance. So this amplify the current, especially in the rotor circuit, and causes the heating, especially in the rotor of this squirrel cage induction motor. So similarly, the DC offset causes the saturation transformer. Harmonics causes increased losses and poor power factor in the distribution system. Interharmonics cause the acoustic noise in power equipment. Notching causes the damage to the capacitive component, and noise causes the capacitor over voltage disturbances to appliances. Another power quality problem as voltage flicker causes the human health effect, irritation, headache, and migraines. And the voltage fluctuations, of course, causes the protection to malfunction, line intensity changes, and power frequency variations causes damage to generator, turbine, shaft, and many other such problems in the system like that. Now we come to the effects of power quality problems on the user. So major financial loss are due to interruption of process, equipment damage, production loss, wastage of raw material, loss of important data. For an example, in automated industrial process, namely semiconductor manufacturing, pharmaceutical industries, where even a small voltage dip or sag has caused the interruption of process for several hours and waste of raw material. Some of the power quality problems affects the protection systems and result in maloperation of protective devices. It interrupts many operations and process in the industry and other establishments. This also affects many types of measuring instruments such as metering of various quantities such as voltage, current, power, and energy. Moreover, these problems affect the monitoring system in much critical, important, emergency, vital, and costly equipment. Another kind of power quality problem, typically the harmonic currents, increase losses in number of electrical equipment and distribution system and causes wastage of energy, poor utilization of utility assets such as in transformer, feeders, overloading of power capacitors also. The noise and vibration in electrical machines, disturbance, interference to electronics appliances and communication network. The power quality problems caused by nonlinear loads results in increased RMS supply current, increased losses, poor power factor, poor utilization of distribution system, heating of component of distribution system, derating of distribution system, the distortion in voltage waveform at the point of common coupling, which indirectly affects many equipment. To continue, the disturbance to nearby consumers, interference to the communication system, interference to the controllers of many other types of equipment, capacitor bank failure due to overload, resonance, harmonic amplification, and nuisance fuse operation, excessive neutral current, harmonic voltage at the neutral point, mal-operation of protection systems such as relay, voltage regulation, and voltage fluctuations. Imbalance in three-phase voltage, derating of cables and feeders. The voltage imbalance creates substantial problem to electrical machines due to negative sequence currents, noise, vibration, power pulsation, rotor heating, of course, their derating. Well, we can classify of these mitigation techniques also of these power quality problems. Broadly classified into the following category. We can use the passive component such as capacitors and reactors for meeting the reactive power and providing the typically load balancing as well as elimination of neutral current under the linear kind of the loads. The second category of custom power devices which are very much in support to come or are already put into practice in distribution system. They are like a DVR, means dynamic voltage restorer, DStatCom, that is distribution static compensator, for making the mainly the current compensation, and the UPQC unified power quality conditioner to meet the both voltage and current power quality problems. If we have a presence of harmonics, of course, in such environment, then the series of power filters are normally used, which are of nature of active filters, passive filters, and hybrid filters. Hybrid filters can be a hybrid of active-active, hybrid of passive-passive, or it can be a hybrid of active-passive, which are considered the cost-effective solution for many situations. We expect in coming time, these are the solution which we call it retrofit solution, but we have the solution for forthcoming generation of equipment, that in many of the equipment we can modify the input stage itself by using a improved power quality AC-DC converters. It means these improved power quality converters at input stage are supposed to eliminate harmonics as well as reactive power burden, provided, of course, by those equipment in which we are using them. There are plenty of examples, maybe a computer power supply, adjustable speed drives. Starting from a fraction of watt to 700 megawatt are the example where we can use or we are using this improved power quality AC-DC converters. So, of course, for some specific example, we can use like a multi-pulse AC-DC converters. Typical example may be a adjustable speed drive, or like an example of HVDC system. Another, of course, the lately, we have a solution of matrix converter, which also can be designed for having a improved quality at the AC supply grid interface like that. Well, now we come to the main theme topic of today, that's the estimation of electrical losses in the distribution system without and with compensators are analyzed using different cases. So what we are considering here is through some typically 4 case study in which we are considering the original application without any compensation or without any compensator, and then if you put the compensator, what is the, of course, reduction in the losses in distribution system. So going to typically a first example, and it's an interesting example only of linear load. So we are taking an example in a 3-phase with a line voltage of 415 volts for 50 hertz, 4-wire distribution system. Typically, let's say we have a single phase load which is connected between phase and neutral and having a current of 100 ampere with a 0.85 lagging power factor. Considering that the feeder and neutral conductor have the resistance of the order of typically 0.08 ohms each. Calculate the AC supply RMS current, the neutral current, losses in distribution system without any compensator, and if an ideal 4-wire shunt compensator is used in parallel to the load to compensate power factor to unity in each phase, then and to balance this load, Then calculate the AC source current, neutral current, losses in the distribution system, rates of losses in distribution system without and with compensator. So now coming to the solution of this interesting problem, given that we have a line voltage of 415, so phase voltage will be 415 by root 3. That comes to 239.6 volt, and the frequency is given 50 hertz, and the feeder, or you can call it the distribution cable, resistance is given 0.08 ohm, and an example, and a single phase load connected between phase and neutral having a 100 ampere, having a power factor of 0.85 lagging power factor. Now the AC source RMS current is 100 ampere. Since it is a single phase load, the same current will flow through the neutral. The neutral current will be also as 100 ampere. Now the losses in the distribution system are calculated as the P loss into 2 into IS square into RS, and that's 2 into 100 square into 0.80. That's a resistance of the feeder equal to 1600 watt or 1.6 kilowatt. This is the losses without any compensation in this single phase load connected in 4-wire system. Now, if we use the 4-wire compensator, which is used typically for power factor correction and load balancing. So after compensation, we expect the power factor is corrected to unity of AC mains by a 4-wire compensator. So 3-phase currents in the AC mains become sinusoidal in phase with the respective phase voltage, and the neutral current becomes 0. In this case, because of loading, this current is divided into all 3 phases of AC mains. The new supply current is an RMS fundamental active power component of load current. We can just calculate it IS equal to IS1 cos theta, which is 100 into 0.853 divided by 3, because this is distributed among all 3 phases now. So it becomes like virtually small corrections like 85 by 3, that's a 28.33 ampere in all 3 phases. And in this case, after the compensation, see the 3-phase current in the AC mains are balanced and sinusoidal. Therefore, neutral current becomes 0 as ISNC equal to 0. The losses in the distribution system now are calculated after the compensation. P loss C, that's for the compensation, equal to 3 into ISC square into RS, that's putting the value of typically of the current and resistance. We get the losses 192.67 watt. So now these losses are reduced from 1600 watt to this value of 192.67 on 193 watt. So taking the ratio loss of the losses without and with, so without compensation losses were 1600 watt, and after the compensation the losses are 192.67 watt. So this is, ratio becomes typically 8.3, or you can call it the losses becomes around 12 to 13%. So these are reduced to 12 to 13% only from typically from 1600 watt to 193 watt or so. It means that unbalanced lagging power factor load caused the increased losses in the distribution system manifold as much as 8.3 times compared to the sinusoidal balance unity power factor loads. So this is a first example. Now moving to another interesting second example, which I have looked into a practical example in the field of a single phase AC voltage controller as shown in the figure, has heating load like a typically resistive load of 10 ohms. Input voltage is 230 volt RMS at 50 hertz. The delay angle of thyristors are used, or you can use the track also, which have a symmetrical firing angle of 120 degree. The feeder conductors are having a ratio of RS equal to 0.05 ohms each. Then we are calculating the AC RMS current, losses in the distribution system without any compensation. And if we use an ideal shunt compensator, to compensate power factor to unity of this load, then calculate the AC RMS current, losses in distribution system, ratio of losses in distribution system without and with compensator. So you can clearly see it when we keep it a firing angle 120 degree. If you look into waveform, the voltage and current will typically will be of the same shape because it is a resistive load, and it will be a part of segment of this sine wave. So now coming to the solution of this problem, given that supply voltage is 230 volt, frequency of supply is 50 hertz, resistance is 10 ohm, feeder resistance is 0.05 ohm, and firing angle is 120 degree, the total resistance of the circuit becomes RT equal to RS plus 2RS because you have a phase and neutral, so it will be 2RS, so total resistance becomes 10.1 ohm. So in the single phase control AC control, the waveform of supply has a value of PS upon RT from angle alpha to pi, and the amplitude of the voltage is 230 into root 2, that's a 325.269 volt. Now the supply current, RMS current, can be estimated by this formula, which is given in many of the typical power electronics books. IS equal to VS into this coefficient divided by RT. So that current becomes 10.0689 ampere. And active power of the load, now becomes IS square R. That is only in the load. So current is square into 10. So that becomes 1.0138 kilowatt. So that's the power consumed, active power consumed by the load. And the losses in the distribution system are calculated as 2 into IS square into RS. So 2 into the current which is already calculated above, 10.0689 square into 0.005, and that becomes 10.138 watt. Now after the compensation, the power factor is corrected to unity of AC mains by shunt compensator, which is used before the AC controller across the point of common coupling. The current in AC mains becomes sinusoidal in phase with the supply voltage after the compensation. Now the new supply current is at the RMS fundamental active power component of load current, that is ISC equal to IS1A. IS1 means supply current, 1 for fundamental, and A for active power. So we have an active power consumed by the load already estimated earlier, that is 1013.8 divided by 230, that's RMS voltage. So after compensation, the supply current reduced to 4.4 ampere. Typically more than 10, earlier it was more than 10 ampere. The losses in the distribution system now are calculated as P loss C after the compensation, 2 into ISC square into RS. So 2 into 4.4 square into 0.045, that's a feeder resistance, and that's equal to 1.936 watt. So now these losses are reduced from 10.138 watt to 1.93 watt, and taking the ratio of the losses without and with compensator now is P loss upon P loss C, that is 10.138 divided by 1.936 equal to 5.236. The ratio is. It means that such a nonlinear load causes increased losses in the distribution system manifold as much as 5.236 times than what could have been after the compensation. A typical note here is the power factor of this type of load is also can be improved by improved power quality AC-DC converters. It means in place of AC voltage controller, we can use some other alternative with improved power quality AC-DC converter. So since it is only the heating load, and used in many applications such as food vending machine, as well as food packing machine, many packaging machine, just for the purpose of control heating. Now coming to another example now, with a typical circuit is shown here. A 3-phase fully controlled bridge converter feeds the power to a load having a resistance of 20 ohm and a very large inductance to result in a continuous current with an input from a 3-phase AC supply of 415 volt, 50 hertz. Feeder conductor have the resistance order of 0.1 ohm each. For firing angle of 45 degree, calculate the AC source RMS current. Losses in distribution system. If an ideal compensator is used in parallel to this converter to compensate power factor to unity, then calculate AC RMS current, losses in distribution system, and ratio of losses in distribution system without and with compensator. If you look into the right side waveform, we have a 3-phase supply, then we have a supply current which is a quasi-square wave with the amplitude of the load current, which is the I0, is shown in the figure like on. So the supply current goes to quite distorted, typically of quasi-square 120 degree width and with amplitude of I0. So now coming to the solution of this problem, given that the supply RMS voltage Vs equal to 415 by root 3, 239.6 volt, frequency of supply of 50 Hz, and the load resistance of 20 ohm and fire angle of 45 degree. So in three-phase thyristor bridge converter, the waveform of AC supply current is Cauchy square wave with the amplitude of DC current, that is I0. The average output current we can calculate from the relation Vd is equal to 3 root 3 Vs upon pi cos alpha, that is 396.2958 volt, and DC link current will be equal to I0 VDC upon RDC, that is 396.2958 divided by typically 20 ohm, which is the load resistance RDC. So the current comes 19.8148 ampere. The AC source RMS current, which is a Cauchy square wave and is a amplitude of this I0, which is we calculate the DC link current, is equal to IS equal to root 2 by 3 into IDC. Why root 2 by 3? Because out of 180 degree it's the only current flowing to 120 degree. So 120 divided by 180 degree to IDC, and that's typically the current 16.17 ampere is the RMS current in distribution system at the input of this converter. So losses in the distribution system are calculated. Since it is a three-wire system, the loss will be P loss equal to 3 into IS square RS equal to 3 into 16.17, that's the current we calculate RMS current square, into the RS, that's a feeder resistance 0.1 ohm, and this becomes 78.5252 watt. After the compensation, the power factor is corrected to unity of AC mains by shunt compensator, which meets the reactive power requirement as well as the harmonic compensation of this non-linear load. So three-phase currents in AC mains become sinusoidal in phase with the supply voltage. So now after the typically coming to the compensation, the net supply current is RMS fundamental active component of load current, that is IS equal to IS1A, again S for supply, 1 for fundamental, A for active component. So it is IS1 fundamental current into cos alpha, that's corresponding to active component. And if we put a relation in terms of the DC current, the derived relation, and this current finally becomes 10.92 ampere. So it reduces from typically that large current of which will be calculated around 16 ampere to 10.92 ampere. The losses in the distribution system are calculated as P loss C equal to 3 IS square into RS, and that is equal to 3 into 10 to the power 9 into square into 0.1. This becomes 35.80 watt. And the ratio of the losses without and with compensator is now P loss upon P loss C, that is 78.5252 divided by 35.8, and that is 2.9132 is the ratio. So it means that the such non-linear load cause the increased losses in the distribution system many-fold, as much as 2.19 times the losses which have under the ideal sinusoidal balance and sinusoidal current, like with the unity power. Now coming to another interesting example, in a three-phase line voltage of 415, typically the figure shown below, 50 Hz 4-wire distribution system, 3 single-phase loads connected to between phase and neutral terminal, having a single-phase thyristor bridge converter drawing equal 30 ampere constant DC current at a 60-degree fire angle of its thyristor, shown in figure. Feeders and neutral conductor have a resistance of order of 0.2 ohm each. Calculate AC source RMS current, neutral current, losses in distribution system. If an ideal 4-wire compensator is used to compensate power factor to unity in each phase, then calculate AC supply RMS current, neutral current, losses in distribution system, and the ratio of losses in distribution system without and with compensator. Now coming to solution of this problem, given that the supply voltage Vs equal to 415 by root 3 V, that is 239.6 volt, frequency of supply F equal to 50 Hz, feeder resistance Rs equal to 0.2 ohms per phase, DC link current of 30 ampere I0, and fire angle of 60 degree, alpha equal to 60 degree. In single phase thyristor bridge converter, the waveform of supply current is a square wave with amplitude of DC link current of I0. The AC source current will be of same as 30 ampere because the RMS is also of a square same as the amplitude. The neutral current will be also 30 ampere since it will also be a square wave of 3 times of fundamental frequency. So losses in the distribution systems are now calculated. C into IS square RS, that is because of 3 phases. And then we have a ISN square RS, the current flowing into the neutral. In spite the balance current, but we have a neutral current also of the same amount as 30 ampere. So that is equal to 3 into 30 square into 0.2 plus 30 square 0.2, that is 720 watt. After the compensation, the power factor is corrected to unity of AC mains by a 4-wire compensator. The 3-phase currents in the AC mains become sinusoidal in phase with the phase voltage, and neutral current becomes 0. The new supply current after the compensation is the RMS fundamental active component of current of load current. IS equal to IS1A equal to IS1 cos L, that is 30 into 0.9 into cos 60, that is 13.5 ampere. So this 30 ampere reduces to 13.5 ampere. And in this case, after the compensation, since the 3-phase currents in AC mains are balanced and sinusoidal, therefore neutral current becomes 0 at the ISNC equal to 0.0. The losses in the distribution system are calculated as P loss C equal to 3 ISC square RS plus ISN square RS. Since so this is 3 into 13.5 square into 0.2, and the neutral current is 0, so that is 0 square into 0.2. The losses are 109.35 watt, and the ratio of the losses without and with compensator are P loss upon P loss C, that is 720 divided by 109.35, and that is 6.5844. So it means that such nonlinear load caused increased losses in the distribution system manifold as much as 6.5844 times. This is the interesting example, but we go through, this is the simplified example, we took it of 4th column, but in practice the load typically like computer load, the neutral current here it is shown equal to the phase current, but in practice the neutral current, is normally many times have been observed around 1.5 times of the phase current, and under extreme cases it can go even √3 times of phase current, that is 1.73 times the phase current. Under such circumstances, you can understand the losses will be much more times in place of the 6.58 times. So that is the very prevailing situation of excessive neutral current in the distribution system due to such nonlinear load on the 3-phase 4-wire system. These are some of the references which refer it, and recently we released the book of this as the last reference of 45 by myself and my couple of co-authors on a power quality, problems and mitigation techniques, published by Joel and Wiley and Sons Limited, UK in 2015. It's long, and this is the cover page of this typical book. So here I conclude my talk. Thank you very much for your patience and listening. So now I pass on back to the
Frank, we cannot hear you. Can you just your headphone?
Can you hear me now? Can you hear me okay? Okay, thank you. So start again. Apologies for that, and I'm not quite sure what happened. So we're going to talk about how we calculate electrical power. And where we're going to start is with the basic used for over 100 years, developed by Steinmetz, which are described as the classical method. This uses two methods in terms of how we can represent apparent power in the system. This one is a simple mathematical sum of the phase powers. This gives you a total apparent power for the system. But if there is unbalance and harmonics present in the system, this can produce some results which are not necessarily correct. The second method, of course, is to do the same summation but vectorially. So the reason why we're doing it vectorially, of course, is that we're looking at the power triangle. So for AC networks, we've assumed for a long time that this was accurate. And for single-phase systems, that's still fine. It still works okay. But when unbalance is present, then there are some potential errors that occur. So in this case, the apparent power, the square of the apparent power is the sum of the power squared plus the reactive power, which I guess we all know for a long time. But then if we look at the phases separately, so first of all we have phase 1, and then we have one power triangle, then we have a second for phase 2, and then a third for phase 3, and now when we look at the total we can see that there is a difference, because if we do the simple summation we don't get exactly what SA, SB and SA are contributing to in terms of the total S, and the same if we do that vectorially, we have a similar kind of error. Because if we look at this, if we think about the powers and the reactive powers, they're always pointing in the same direction and can be added simply, so the magnitude doesn't change. But because the apparent power has a direction too, and depending upon what that phase angle is or power factor in the system, that can affect exactly the magnitude in terms of the overall capability of that power. So we have a situation where potentially we're overstating the apparent power, which obviously can cause cost implications, and the likelihood that we maybe overinvest or underinvest, and making sure that we're keeping the electrical network as healthy as possible and as efficient as possible for the right amount of money, of course. So in this case, we'll just mention that the S1 value here is the fundamental apparent power, and we'll come to that into the next method that we'll talk about. And the next method is the IEEE 1459 method. This method is something which is really developed over quite a few years now and is well accepted, but there is an acknowledgement that there are certain balances and checks here that we have to consider. The title of this standard is a very long one. It's definitions of measurement of electrical power quantities under sinusoidal and non-sinusoidal balanced and unbalanced conditions, which suggests that a lot of thought has gone into all of the calculation methods, and it's quite an academic piece of work, but it relies on some mathematical tricks really to discover what the power is. And unfortunately, because of that, those mathematical tricks or system apparent equivalent system methods are not necessarily present in every electrical system or in any electrical system. So the question being, well, why did IEEE 1459 develop? Well, one of the reasons was, of course, that the potential accuracies in the classical method have been recognized for a long time. So going back to the 1920s, these were recognized. And other electrical engineers and physicists have tried to make changes to fix these problems over time. And this is a good way to get to the required changes. The 1459 was developed in the US with predominantly by Professor Alex Emanuel, who led a team of academics, utilities and industry from around the world to come up with a solution that would be could be reasonably used to model the system. And the original standard was released in 2000, so in the late 90s all of this work was being done. As the increase in power quality problems appeared, so it became clearer that the need for a different way of describing the electrical system and quantifying losses had to be developed. So I've already mentioned that there is some problems with 1459. The first one, I would guess, for most people is that because it uses this virtual replacement system for unbalance, it has a certain level of complexity which creates a set of boundaries that are not always present in real installations. So you have to make some assumptions at the start that you are within the boundaries of the replacement system, but you may not be. The biggest problem, of course, is that it produces some errors in apparent power calculations when severe unbalance is present, because the unbalance is only allowable within a certain range. And finally, although the system of the IEEE 1459 develops lots of different values, sometimes the physical significance of those values is not necessarily that clear. They are predominantly used for calculations or sub-calculations through the system, which is helpful to a certain extent, but in terms of practically applying this in the field, that becomes difficult. So to that end, we kind of discovered some work that had been done in Europe, and this is a method described as the Unified Power Measurement Method. And the idea behind this is that it uses a real electrical system. It calculates apparent power based on the instantaneous voltages and current relationships, and it works with severely unbalanced systems. So this work around unified power, it is based upon the 1459, but it addresses the issue of unbalance in the system. It was developed by Professor Vicente Leon and Joaquim Montaya in Valencia. The method unifies the various power theories and the results are compatible with 1459, but the method breaks down the total power into different physical components which can then be seen as significant and which can help gain some further insight into the system in terms of the effects of unbalance and in terms of effects of harmonics. So in the simplest terms, the physical components that we pull out, we consider the effects of first of all, of harmonics, and we break this down into the fundamental power, the full power, and the harmonic power. And these are terms which are described in 1459, but are not necessarily pulled out in exactly this way. And then the other area, of course, is the unbalance. So breaking down into these separate components allows us to consider mitigation for each of the effects separately. So it may well be that harmonics on the system are the biggest problem, in which case you don't need to mitigate for unbalance, or it may be the other way around. But understanding exactly where the losses are coming from enables you to intelligently decide whether the return on investment for installation of filters or other compensation devices is worthwhile. If you can quantify what the losses are and you can see how much that costs over time, then it makes the investment decision that much easier. So we'll just have a quick run through here of the comparison of the methods. I won't go into all of the detail of exactly how IEEE 1459 operates. but I will just go through some of the basics here about the key error, which is when you have severe unbalance. So in this example, we have 3 simple lighting loads. By the way, some of the things here you may not be familiar with. They are included in the IEEE 1459, but I'll give you a broad picture of kind of what happens here. So these lighting loads, when they're balanced, everything looks okay. But say we were to lose one of the loads, so say lamp 1 burns out, so that the active system power is now the only power remaining from the 2 lighting loads, or in this case 2.4 kilowatts. The apparent power from the unified method is not now 2.4 kVA or the classical method, but it's actually measured as 2,939 watts. So we can see that in this box here. Oh, sorry. We can see that here. And now the difference goes into a larger value of unbalanced apparent power. And the unified method calculates the unbalanced apparent power as 1,697 VA. And this is because the 3-phase generator is determined to deliver 3-phase power with same phase voltage and same currents. And because of that, when one lamp fails, the 10 amps that's in the phase drops to 0, instead of you suddenly have 10 amps flowing in neutral, which is a bit of a surprise. The fact of the neutral flowing is in itself a sign that not all is well. So neutral is a reference point, is not supposed to carry current except when there's a fault. So the various methods differ in the way they calculate the apparent and unbalanced apparent powers, which are described as S and S1U. The difference is mainly caused by the way the 10 amp neutral current is included in S in the IEEE calculation. So the different S leads to different unbalanced apparent power. One of the things that does exist is that a number of these values that we see here, so we have S1U squared, apparent power squared, and then the component which is the IEEE 1459 S1 plus squared, which both unified and IEEE 1459 agree on. The classical method just adds up the phase apparent powers arithmetically and ignores the influence of unbalance. That suggests that imbalance has no effect on the apparent power and the fundamental power, which in this case is incorrect. So the unified approach uses the Buchholz approach, which was originally developed in 1922 for the treatment of apparent power. The maximum possible active power transmitted to load for a given voltage waveform, and adds the apparent power in the neutral conductor. Now the positive sequence currents not shown in the diagram are 6.67 amps, the negative sequence currents are 3.3 each, and the zero sequence are a third of the fundamental, or 3.3 as well. Because the neutral is multiplied by the voltage across the neutral conductor to find the apparent power component, this has only moderate influence on the overall apparent power S. So that gives the 1,607 VA unbalanced power for S1U in the last picture, or in this diagram. So IEEE 1459 introduces the effective power. That's actually SE. It's mathematically sound and complete, but it's hard to read for a non-mathematician, and some of the parameters associated with the effective power are difficult to link with real physical phenomena. So it multiplies the neutral current by all the phases and phase-to-phase voltages, which results in a heavy influence on the neutral current on effective apparent power and effective fundamental apparent power. For that reason, it gives a high value of apparent power, and the high value in this case is 2,683 VA for the unbalanced power in this example. So what's the best approach? Well, that depends on your point of view as much as anything. For an engineer, it's hard to see why current in the neutral why the current, the neutral current which will flow through the branches, has to be multiplied by voltage that has no relation to it, as in EEE 1459. The unbalanced power information in the unified method allows us to use passive unbalanced compensation techniques, while the EEE 1459 method leads to unbalanced compensation that consumes more overall active power. So here we'll just look at a simple practical three-phase losses. In this example, we're discounting the line losses from the utility. So we're just assuming here that we have a point of common coupling, or the metered point here, and then we have some loads in the system. So we have the cables which are feeding the loads, and we have the voltages which are coming through, and we have three phases plus neutral. So according to the IEC publication Efficient Electrical Energy Transmission Distribution, the overall loss between the power plant and user can be easily between 8 and 15%. Overhead land for about 2.5% of that loss, and then the transformers which step down the voltage between 3 and 5%. On average, the losses are double those between the substation and the user. So the publications mentions three causes of these losses. First is the Joule effect, where energy is lost as heat in the conductors, or there's magnetic loss where energy is placed into a magnetic field, and then there's a dielectric effect where the energy is absorbed by the insulating material. Here we'll focus on the line losses, and particularly the line losses at the user side of the system. I know that we have some utility people on board today, but we predominantly work with industry, and that's why we like to talk about the losses within the facility, because that's where the power quality problems predominantly appear, because the system inside of facilities is quite a lot more difficult to manage because it's constantly changing, whereas the utilities network is very heavily managed. They can bring compensation on quite easily. They still may have losses, but they have a much clearer view of their network. So we'll go inside the facility for this example. So the losses obviously will have an effect on the electricity bill. And at the end of all of this, although we're doing calculation and engineering, that's what we're really interested in, is how much it's costing and what the efficiency is. So in this diagram, it shows a general line loss situation. Currents flow through non-ideal conductors, which have a certain resistance. In general, the phase conductors will all have the same line resistance because they have equal length and cross-sectional area. The neutral current, however, can have a different cross-sectional area and can have a different resistance. As the currents flow through the line resistance, heat is generated according to power. Heat is equivalent to I squared R. That's the active power supplied by the source but lost to the load. And although there are losses throughout the whole of this system, as a consumer you'll be more interested in those losses on your side of the meter, so we effectively, as I mentioned, ignore the utility losses. So the unified method does something somewhat different from the other methods. So we effectively decompose the current. So here we're looking at, we have small I and large I here. So the small I are instantaneous values and the big I are the system values. So we look for each of the phases and we can break down each of the losses into these separate composition. Here where they're called IX, so X is the name of the feeder, that's A, B, C, or L1, L2, L3. And we break these down into the phase active current, the phase reactive current, the phase unbalanced current, and the phase non-fundamental current. So non-fundamental being any harmonics, for example. So as we break those down, well, why do we split them into these parts? Well, this is going to give us a good indication as where to look for improvements. So if we don't like the outcome of the total line loss, we can look at exactly where that line loss is coming from. So to calculate the total power loss in the transmission system or local distribution system, we could add together the squares of the RMS values of the individual current components and multiply each one. That need a lot of calculation, so we developed this shortcut. So by defining the system current IL, we can quickly calculate the system level RMS values of the phase current by category. That's active, reactive, unbalanced, and non-fundamental. The system current is derived from the symmetrical currents, that's the positive, negative, and zero sequence currents, which are also system currents, and combine into a fundamental frequency current phenomenon. And then we only have to use a separate mathematical method for non-fundamental current. So if we look at the bottom of the screen, we see the system currents. So the system current is shown lower down. Beware that this current IL is not a physical current but a mathematical shortcut. It allows us to calculate the effect of the individual phase currents. Once we've calculated this system current IL, calculating the total power loss caused by the phase currents is straightforward. It's simply the loss is equivalent to 3 times IL squared times the resistive load. So in which the resistive load in that case is the local distribution cable. The factor of 3 is because we have 3 phase conductors. However, there is also a neutral line which can carry current. It should ideally be 0, but it may not be, and that will also cause dual losses, I squared R losses, in the neutral resistance current, neutral conductor resistance, and that will also appear on your electricity bill. So the complete calculation here that we present is that we have power loss is equivalent to 3 times the IL squared times RL, that's the phase conductor resistance, plus the neutral current times the neutral current conductor resistance. That's I squared for the neutral current, of course. So now we'll look at these at the system levels, so through this decomposition method. So we start at the phase level. So here we have the currents that I already mentioned, I for each one of the phases plus the neutral. Then we break this down into the fundamentals, and then we go then to this system level, which allows us to consider the symmetrical currents for negative, positive, and zero sequence phase. And here we lose individual information and talk about values that are only meaningful at this system level. And then we further break those down into active, reactive, unbalanced, non-fundamental, and neutral. So the IL, or the IL squared, is equivalent to the summation of each one of these, the active square of, or the active square of I1A plus, that's positive sequence, and then reactive, and then the unbalanced, and the non-fundamental, and then the neutral. Again, it excludes, we're excluding the current which is processed separately, so it comes directly from the phase level, the neutral current. Once we've determined what the IL is, then we can calculate the various losses from the physical phenomenon. The line loss due to the active current is unavoidable, and they can only change that by having thicker conductors, which typically is not economically feasible unless you're really close to the limit on it. The loss due to the reactive current can be reduced by compensation, by reducing the phase shift between fundamental voltage and current using compensation capacitors. The loss due to non-fundamental currents can be reduced either by avoiding generating, that's not generating harmonics, or by using passive or active filtering, or a combination of. And the loss due to unbalanced current, again, can be reduced by balancing the system or compensating again. And the loss due to neutral current can be reduced by not generating neutral current in the first place, and as that's usually mostly from the result of harmonics or unbalance, if you take those other steps, then the neutral current is going to be low. So a further breakdown of where the losses are. So if we look at the dual losses, so this is basically how we look at it, and we have the separate losses due to active current, reactive, harmonics, and then loss. So here we have a sample of a energy loss calculator that we've developed, and here we see the components broken down for each of the elements. So we have, first of all, the active power. In this case, we describe this based upon 25.6 kilowatts. This is based upon the length of the conductor that we're considering and the diameter and also the material, whether that's copper or aluminium. Then we have the reactive power, and again we have the same calculation of losses. Then we have the unbalance power and the loss caused by the unbalance, and then the distortion or harmonic losses, and then finally the neutral. And in this case we're making a calculation. This is a simple calculator. We're currently improving this, but it uses the unified power method to take each of the separate components so that we can really make a good judgment as to where you should make investments in your electrical system. So just a quick description of some examples now. So whilst this example was developed or was made when they were developing the unified power method, some of the lessons learned here, I think, weren't necessarily required the unified power system. I think probably by careful management of your loads, you could really do the same thing. So in this case, this industrial part made an annual energy saving of $14,000 or euro equivalent, and this was because of measurements were made at substation, transformer, feeding, and industrial part, where the energy losses were averaging 350 kilowatts per day due to reactive power. And the way to reduce that reactive power was by disconnecting the capacitor bank at night, because it was just consuming energy effectively. The second one here, I think, is really key when considering power quality. We can immediately see it says the survey went across 6 areas of this engine plant and car assembly. Significant energy waste down to power quality. So measuring and monitoring is key, and also doing this on a fairly regular basis, because the loads change in the plant, the processes change. In this case, they managed to come up with $50,000 in energy savings, and the solutions were by installing capacitors and voltage regulators, upgrade of transformers, and really looking at the infrastructure and making sure that they had the right equipment for the new tasks that were being handled inside the plant. So, quick summary: poor power quality does have an effect on system efficiency. Harmonics and unbalance increases losses. Choosing a practical method is really important, because you want something which is not going to take up too much of your time, that you can understand what's going on, you can pinpoint the areas where savings can be made and efficiencies can be taken out. Making sure that you're using the right method and recognizing that there are potential errors in your calculation method is important. And you know, to that end, IEEE 1459 is being revised to account for those errors. Last things are, mitigation is often complex, and first of all, you're best starting with best insulation practices to minimize losses. If you size your conductors correctly and you balance your loads properly, then you have a much stronger opportunity to come up with an efficient electrical system. It's impossible to have zero line losses. You have to accept that there will always be some line losses. But one of the things is you should be looking at mitigating the major sources. It may well be that you have to do a Pareto of which are the significant contributors to energy efficiency losses and which ones can be maybe left in place. So by doing that, you can look at mitigating locally, for example, at one machine or 2 machines. And again, just to repeat, frequently consider the potential losses. Don't assume that the electrical system is a static thing. As you know, machinery is changing all the time, processes change all the time, and that can have an effect on the overall efficiency. Thank you. Okay, I think we have questions now, is that right?
Yes.
Okay, there is a question. Dr. Bhim Singh?
Yes, yeah.
How to minimize alternating current voltage fluctuation?
How to minimize the voltage fluctuations?
Fluctuation. Yes.
Okay. Well, normally the voltage fluctuations. Can I answer now?
Yes.
Hello?
Please go ahead.
Okay.
Please go ahead.
Okay. Normally the voltage fluctuations may be because of the two reasons. One is because of the supply system, and another is because of the load. So if we have a fluctuating kind of the load, then we can have a voltage fluctuations at the point of common coupling, which is experienced by other consumers. That is one reason. Another reason for voltage unbalance or voltage fluctuations, like it may be because of the typically from supply system, which may be from the back of supply system. Well, this voltage fluctuations up to, if it is because of the load, by providing the shunt compensator, this fluctuations also of the voltage also reduces. So it depends that because of which these voltage fluctuations are there. Whether it is because of the load or because of the supply. Okay, if it is because of the load, then if we compensate up to some extent, like furnaces kind of load, then this fluctuation, voltage fluctuations also reduces. But if it is because of the supply, then we have to use some kind of series compensator, which I just mentioned in initial slide, like maybe a DVR, dynamic voltage restorer. That's the device or equipment, you can call it, to compensate for voltage fluctuations and provide the regulated voltage across the load. I hope probably the partially, because however, it is not in the scope of the today topic how to calculate the electrical losses due to poor power quality. But I thought it okay to some extent. Yeah.
I agree.
Okay, thank you.
So, any other question?
So what is the another question? Like I'm not able to see.
No, I'll transfer that question if anything coming here.
Okay.
There is a question. What all regulations are there in India for power quality?
Oh, anyhow, we don't have any. As far as my knowledge is concerned, there are not much. Standard regulation of power quality in India, but there are individual some regulations. Typically, like maybe a lighting system. Okay, they have put some standard for lighting system. They have put some typical standard for voltage fluctuations. Like typically in urban areas, earlier they used to say plus minus 6%, and for typically for rural area they say plus 6% and minus 15%. Because in rural areas it is very difficult to maintain the voltage level, lower voltage level, of the order of plus minus 6%. So that is about voltage. But if I correctly remember, for lighting system, I think they were having some time that on the total harmonic distortion as well as on power factor. So there is a regulation on power factor, of course, that typically the penalty is there on the power factor. If I'm correct, I think some of the utility are putting a penalty, power factor goes below 0.85. But yesterday we were in in some discussion where the power factor is recommended above 0.9. The question is, one is that if it is a penalty, then you have to improve. Okay, if it is not a penalty, then you may not get an incentive to improve it. So, these are the at the moment situation, but we don't have any such standard like which probably may be about the harmonics or the power factor, maybe in like North America or Europe. Like I think that is as far as my knowledge is concerned.
Okay, I might supplement. Yeah, I may supplement on this. As far as grid level, there is IEGC, Indian Grid Code, and that grid code as well as at the state level, there are supply code which mentions about power quality, but the regulations are normally enforced at grid level, not at the distribution sector level. So we have to actually come to that regime where at the distribution sector level, regulations have to come in place. Now the next question addressed to Mr. Frank.
Actually, I just had something. I just had something to add on that last point. I am aware that some utilities in India are now using IEEE 519 as the basis for harmonic reporting. So if you're a facility that's connecting to the grid, some utilities are saying that you have to be within the limits of the IEEE 519.
Yeah, that is reflected in the IEGC, the Indian Electricity Grid Code.
Okay. Okay.
Okay, so the next question comes to you, Frank.
Yes.
Are there any existing or upcoming monitoring devices which could monitor the harmonics on continuous basis and act in conjunction with other protective devices?
That's not something that we do as an organization. We're more focused on portable equipment. I know that there are that kind of devices out in the world, but it's not really our speciality.
Okay. So then another question, how do we measure the unbalance in the system?
Is that to me?
Yeah, that is to you actually. How do
Okay.
we measure the unbalance in the system?
Well, are we interested in unbalanced voltage or unbalanced current? So you can measure both things, obviously. Many of the electric codes that exist around the world primarily focus in on unbalanced voltage. The reason being that if the voltage is unbalanced, that can cause problems with some of the rotating loads like motors, and also can cause problems with transformers. The unbalanced currents are measured obviously separately. It's relatively straightforward to measure the currents. The overall problem, I guess, is then measuring the effects of those in terms of system efficiency, and that's why we look at the loss analysis that we do and the way that we calculate either using IEEE 1459 or using our unified power method.
Thank you, Frank. The next question comes to Dr. Veem Singh. Can you please elaborate more about the matrix converter? Can you please elaborate more about the matrix converter?
Okay. The matrix converter is a converter which is a matrix of the devices, and we consider it that it can convert all four conversion: AC to AC, AC to DC, DC to DC, and DC to AC. However, for three conversion where the DC is involved, typically like AC to DC or DC to DC or DC to AC, we have another converter much better than matrix converter. Okay, but only AC to AC, we use the matrix converter. So the matrix converter is you can call it a kind of replacement of cycloconverter with improved power quality on the input side. Means you can have a harmonic reduction to a standard like maybe less than 5%, which is IEEE 519, and we can have a displacement factor or power factor close to unity in matrix converter. In spite, you can change the voltage level as well as it can change the frequency from fixed frequency input AC mains to the variable frequency, variable voltage, which may be used for many applications such as an adjustable AC drive, maybe variable frequency drive. So that's what we call it, the matrix converter. I hope it is partially.
Thank you, sir. Thank you, sir.
Okay, thank you.
There is another. So, we know the firing angle to calculate the losses.
Yes.
In a practical system, fire angle for calculating the losses.
Yeah. Sorry, I think there is some confusion. I'm not able to listen fully. Can you repeat?
Should I repeat? Yeah. In a practical system, how do we know the firing angle to calculate the losses? I think this question is not well understood.
I am able to follow now the question. Probably the question is that, okay, in a practical system, how to really measure the firing angle? Okay, that's the question is, no?
Yeah.
Okay.
Yeah.
The reason, Yeah, so it depends on the kind of device. An example I have given, typically couple of examples where the firing wheel were involved. Typically in single phase AC controller, okay, the firing wheel easily can be, one can see clearly by looking the voltage waveform, okay, and enlarging the voltage waveform, that form where this voltage is going to be from 0 to the normally on AC wave. So from the zero crossing of the voltage of input supply voltage, and where this changeover is taking place from the voltage appearing across the load, so you can easily find out what is the firing wheel like. Of course, this may be a very simple approach, but other approach, of course, if you know probably the parameter of the system, so one can find out easily by doing calculation, but the calculation involved may be little bit more involved in that, if it is about AC control. But if it is a thyristor converter, which I've given an example, there we can easily find out from, if you are measuring active and reactive power, okay, and you are measuring other parameters, so you can easily calculate the firing wheel easily from that without any much difficulty. Okay, I think it's okay. Thank you. Okay.
Yeah, thank you. Frank, this is for you.
Yeah.
From an energy auditor's perspective, how to calculate the losses due to harmonics and unbalance in any PCC in an industry?
Well, the first point of that is to discover, using something like the unified power method, to break down into each of the separate components. That's the harmonic and unbalanced losses. But I would also, looking at the point of common coupling is certainly one approach. However, over a lot of years of experience with customers and our equipment users, they find that really breaking down the whole of the facility is the best way to approach this as a problem. So going to individual loads, looking at which are the biggest loads and which are the most affecting loads, which ones have got most unbalance, which one have got most harmonics. Looking just at purely at the PCC can result in compensating for an overall compensation, but the efficiency still inside the plant is not necessarily that high. So for example, if you put power factor correction at your PCC, you still have significant losses inside your system that you're not accommodating for, you're not mitigating for.
Okay. The next question to you again. How one can calculate average power factor of three-phase unbalanced system?
Average power factor. Well, the way that we approach all of our calculations is that first of all we take instantaneous values, and we make our measurements in accordance with the IEC 61000-4-30 standard. That standard has been developed over quite a few years now, and it's essentially a guide to how you should make measurements and how you should represent them. So what the standard suggests is that you take your samples and then you consider every half cycle, which gives you, it's either a half cycle or a full cycle depending upon which method you want to use, which gives you a value for that particular cycle or half cycle, and you consider what the minimum maximum is and the average for that cycle. You then take all of those values over a 200 millisecond period if you're operating at 50 Hertz, and you then average all of those values and you get the minimum and maximum of all of those values. So that's a 200 millisecond value, and then over the longer period of time you then consolidate those into 10-minute values, and each time you're taking averages. You're not losing any data. That's the key thing, that you're continuously sampling and you calculate next average and next average and next average.
Okay. Thank you. This is for Dr. Singh. In saturation condition of motor, we know that line current THD increases with increase in the voltage across the motor. But after certain level of voltage, is line current THD decreases with increase in the voltage across the motor?
Well, with the increase in the voltage, I mean, because of saturation, of course, you will find the harmonics or total harmonic distortion will increase. But I don't think that by increase we will not be able to go that high voltage normally, where the total harmonic distortion by increasing the voltage start reducing. So that condition normally we don't have. Okay, so if voltage reduces, of course, certainly the total harmonic distortion reduces. Okay, or typically we have little increase in the load. That's also responsible to reduce of the harmonics in the voltage. Like I hope it is.
Okay.
I think let me read the question. We know that the line current TAD increase with the voltage across the motor. Certain level of voltage, it is the line current decreases with increase in voltage across the motor. Condition, we know that the line current TAD increases with increase in voltage across the motor. I'm not like much aware that if after certain increase in voltage TAD reduces. I'm like,
okay.
In general, we say that TAD increases by increasing the voltage because of the saturation. Okay. Thank you.
Okay. Okay. The next question again to you, sir. Is compensation technique equals to supply of reactive power to the load, which will result in unity power factor? Of course, yes.
Yeah, means we can, of course, if it is only because of reactive power, by compensating reactive power, you can have the unity power factor. But I think more the emphasis is like maybe if it is a load unbalance, the reactive power can provide the balancing even if the harmonics are not present. Like, so one can separate out the problems. Like one is only, let's say, reactive power, another is the negative sequence current or unbalanced current. That also can be compensated the reactive power, unbalanced reactive power, like something like that.
Okay. Now the next question comes to Frank. If motor is running with VFD and at 40% loading, what is the effect on harmonics level?
Could you just repeat the question again, please?
If a motor is running with variable frequency drive, and at 40% loading, then what will be the effect on harmonics level?
Harmonics level on the system really depends upon the design of the drive, because if you have a well-designed drive, it will have filtering on the front end, so that the system doesn't see any of the harmonics, and that they're contained within the drive system itself. If you have a poorly designed drive, then it could be significant, but it all depends upon the type of drive.
So the loading really, it is a design which affects the harmonics level in a drive, right?
Yeah, the designer of the drive should be considering mitigating what happens when harmonics are present. Harmonics will always be present when you have VFDs. However, that doesn't necessarily mean that those harmonics are fed into the system. They can be contained within the drive system with good design.
Okay. Then the another question which is coming to you, do you have any loss calculator?
Do we have a loss calculator? We are currently developing a set of materials which will detail exactly how our loss calculator works. We expect to be launching that next year and providing seminars on that subject. So we do have a loss calculator, but I can't show you it today.
Okay, great. Definitely they will join at some other occasion. We can do that.
Yeah.
Another question which comes to Dr. Singh.
Yes,
can
please.
there be less currents? Can there be less currents due to power factor corrective component like hybrid filter? Can there be loss current due to power factor corrective components like hybrid filter?
Yeah, so hybrid filter depends. Like it can certainly improve the power factor, and normally depends. If you are considering only the filter is supposed to only reduce the harmonics. But if you are taking a reactive power from it, of course, if it is using a passive filter part of hybrid filter, normally part of reactive power it compensates, because normally in passive filter we use a capacitive element. So that gives the fundamental reactive power at fundamental frequency. Okay. So that also can compensate reactive power. But it can be other way around also. If you have a light load condition, it may happen that it may have excessive leading reactive power also. So one have to be little careful that how we are designing the passive filter and what kind of application we are talking about. Like, okay. So one have to really see carefully about it. Okay, thank you.
Thank you. Frank, we have another question for you. What is the permissible limit for unbalanced load?
Sorry, what is the which limit?
What is the permissible limit for unbalanced load?
Permissible. Yeah, it depends who's permitting things to happen. In Europe, we have the EN 50160 standard, and they're suggesting at low voltage it's 2%.
Okay. There is another, I think this is, I have a scope to address one or two questions maximum, but one question which is looking to be generic. The question is, can you recommend us with some product which can help home and business users to reduce electric losses? I think we'll refrain from answering this question, but yes, there are products, but it all depends on the application, and it is beyond this scope, so we can take it offline sometime. You are welcome to post that question offline. And if you have any other questions, I think we have already covered our time, so we'll take it later, and you can post those questions, which we will of course see that is answered or hosted on the website in form of a question answer and post webinar after within a week of time or so. And after the webinar, we are also requesting you to participate in a survey. So with that, I once again thank my experts for having taken time to interact with the audience and APQI community at large. I also thank all the attendees for having patience and shown a great encouragement in participating in this webinar, and we call the day now here, and we call the session closed. Thank you once again.
You're welcome. Thank you.